Hello everyone, and welcome to our lesson on how to understand basic solar power electrical equations, a beginner's guide. In this video, we're going to break down the essential electrical equations used in solar power systems, explain what each term means, and show you how to apply these equations to design and understand your solar setup. Whether you're a hobbyist or just curious about solar energy, by the end of this lesson, you'll feel confident tackling these equations in a simple, step-by-step way. Let's dive right in. Before we get started, it's important to know why these equations matter. When building or troubleshooting a solar power system, understanding how voltage, current, power, and resistance interact can help you optimize system performance, calculate energy needs, and ensure your components work safely together. Think of these equations as the language of electricity. They help you talk with your solar panels, batteries, and inverters. Let's begin by defining the basic electrical quantities. First, voltage is the electrical pressure that pushes electrons through a circuit, measured in volts. Imagine it like water pressure in a hose. The higher the pressure, the more forcefully water is pushed out. In solar systems, voltage tells you how strongly the solar panels can push electricity. Next, current is the flow rate of electrons, measured in amps. Using our water analogy again, if voltage is the pressure, current is the amount of water flowing through the hose. In a solar panel, current indicates how many electrons are moving at any given moment. Then there's resistance, which is the opposition to the flow of current, measured in ohms. Think of resistance as the narrowness of a hose. A narrower hose makes it harder for water to flow through. Resistance in electrical circuits can limit the current, affecting overall performance. Finally, power is the rate at which energy is used or produced, measured in watts. In our water analogy, power is like the work done by the water, such as turning a water wheel. In solar power, power tells you how much energy your panels are producing at any moment. Now that we know these basic terms, let's look at the key equations. The most fundamental equation is power equals voltage times current. This means that if you know the voltage and current of a system, you can calculate the power output. For example, if a solar panel outputs 20 volts and 5 amps, its power output is 20 multiplied by 5, which equals 100 watts. This equation helps you understand how much energy you're generating at any given moment. Next up is Ohm's law. Voltage equals current times resistance. This simple formula lets you calculate any one of these three values if you know the other two. For instance, if you know the current flowing through a circuit and the resistance of that circuit, you can find the voltage. This law is crucial when you're looking at how the components in your solar system interact with each other. Another useful relationship involves energy over time. If you want to know how much energy is produced or used, you can calculate energy equals power times time, typically measured in watt-hours. This equation tells you the total energy generated by a solar panel over a period of time. For example, if a panel produces 100 watts and runs for 5 hours, it generates 500 watt-hours of energy. Let's see how these equations come together in a solar power system. Imagine you have a solar panel that produces a certain voltage and current. Using the power equation, you can quickly determine its output. This information is vital when you're comparing panels, sizing your system, or matching your panels with batteries and inverters. If you want to store energy, you need to calculate how many watt-hours your battery bank should hold based on your energy needs. For instance, if your daily usage is 1,500 watt-hours, you'll need a battery system that can safely store that amount, considering some extra capacity for inefficiencies and losses. Now, let's explore a practical example together. Suppose you have a solar panel rated at 250 watts. Often this rating is given at standard test conditions. If the panel operates at 30 volts, you can calculate the expected current output by rearranging the power equation. Current, I, equals power, P, divided by voltage, V. In this case, 250 watts divided by 30 volts equals about 8.33 amps. This simple calculation helps you understand the panel's behavior and determine how many panels you might need in parallel or series to match your system requirements. Speaking of series and parallel connections, let's talk about how these configurations affect your system. When you connect solar panels in series, the voltages add together while the current remains the same. For example, if you connect two 30-volt panels in series, the total voltage becomes 60 volts, but the current stays at 8.33 amps, using our previous example. This is useful when you need to match a higher voltage requirement, such as charging certain battery banks or running an inverter. On the other hand, when panels are connected in parallel, the currents add together while the voltage stays the same. So, if you connect two panels in parallel, you'll still have 30 volts, but the current will double to about 16.66 amps. Understanding these configurations is key to designing a system that meets your voltage and current needs without overloading any component. Let's delve a little deeper into Ohm's law with another example. Imagine you're troubleshooting a component in your solar system and you need to know if a wiring section is correct. If you measure a current of 4 amps flowing through a wire with a resistance of 2 ohms, the voltage drop across that wire should be voltage equals 4 amps times 2 ohms, which is 8 volts. This calculation can help you verify if your system is performing as expected or if there might be a problem with the wiring or connections. Understanding these equations isn't just about numbers. It's about gaining insight into how your system functions. When you know the relationships between voltage, current, resistance, and power, you can make informed decisions about which components to use, how to configure them, and how to troubleshoot issues. It also allows you to predict how changes in one part of your system can affect the overall performance. Let's pause for a moment and consider an interactive challenge. Think about a solar system you might want to build. Write down a hypothetical scenario with a set of solar panels, estimate the voltage and current, and calculate the power output. Then imagine connecting these panels in series and in parallel. How does the overall system voltage and current change? This kind of hands-on exercise helps cement the concepts in your mind. As we move further, let's consider energy storage. Batteries are a critical component in many solar systems, especially for off-grid setups. When sizing a battery bank, you'll often use the energy equation. Energy in watt-hours equals power in watts multiplied by time in hours. For instance, if you need to power a small system that consumes 500 watts continuously for 4 hours, you'll require a battery bank that can store at least 2,000 watt-hours, ideally more to account for efficiency losses and depth of discharge limits. By understanding this equation, you can choose batteries that are appropriate for your energy demands and ensure a reliable power supply. Another concept to understand is efficiency. No solar system is 100% efficient. There are always losses due to wiring, inverter conversion, and battery charging or discharging. Efficiency is often expressed as a percentage. If your system has an overall efficiency of 80%, then only 80% of the energy produced by your panels is usable. While we won't dive too deep into complex efficiency calculations today, it's important to recognize that efficiency factors into your energy production and storage calculations. Before we wrap up, let's quickly recap the main equations we've covered. Power equation P equals V times. This tells you how much power is produced or used based on voltage and current. Ohm's law, V equals I times R. This equation helps you understand the relationship between voltage, current, and resistance. Energy equation. Energy in watt-hours equals power in watts times time in hours. This is crucial for calculating how much energy your solar system can produce or store over time. Series and parallel. Configurations. In series, voltages add, current remains the same. In parallel, currents add, voltage remains the same. By mastering these basic equations, you're well on your way to designing a solar system that meets your specific needs. Remember, these equations are tools that help you predict system performance, identify potential issues, and optimize your setup for efficiency and safety. As you continue your journey in solar power, I encourage you to practice these calculations regularly. Try creating your own sample scenarios, experiment with different configurations, and even challenge yourself with real-world examples. The more you practice, the more comfortable you'll become with these concepts, and soon they'll feel like second nature. Thank you so much for joining me in this beginner's guide on basic solar power electrical equations. If you found this video helpful, please hit the like button, subscribe to Van and Dan Academy, and share your questions or experiences in the comments below. Your feedback not only helps us improve, but also builds a community of learners passionate about renewable energy. Until next time, keep exploring, stay curious, and happy calculating. Thank you for watching.